Have you ever caught a snowflake on your glove and wondered how something so delicate could exist? How does water, that simple substance you drink every day, transform into such elaborate architecture? What if I told you that within each tiny crystal lies a story written in molecular bonds, a tale of temperature and time, of chaos and perfect symmetry? For the next hour, let us slow down together and enter the quiet world of ice, where we will discover that the smallest things can hold the greatest wonders. Join me on this peaceful journey into the heart of winter itself. Every winter, billions upon billions of snowflakes fall from the clouds above us. They drift down through the cold air, tumbling and spinning, catching the light in ways that make them seem almost alive. Each one is a temporary visitor to our world, existing for only moments before melting away into memory. But in those brief moments, they represent something profound. They are proof that nature can create infinite variety from the simplest ingredients. Water and cold air, nothing more, yet from these humble elements arise structures of breathtaking complexity and beauty. You have probably heard it said that no two snowflakes are exactly alike. This is more than just poetry. It is a mathematical truth born from the nearly infinite number of paths a single ice crystal can take as it grows. Think about that for a moment. Out of all the snowflakes that have ever fallen, that are falling right now, and that will fall in the future, each one carries its own unique fingerprint. What makes this possible? The answer lies not in chance, but in the very architecture of water itself, in the way molecules arrange themselves when they freeze. Before we can understand how snowflakes form, we must first appreciate where they come from. High in the atmosphere, far above where planes fly, water exists not as liquid but as vapor, invisible and dispersed among the air molecules. Up there in the frigid reaches of the troposphere, temperatures plummet far below freezing. It is in this hostile, beautiful realm that our story begins. When conditions are just right, these scattered water molecules begin to find each other, drawn together by forces we will soon explore. This is where the architecture begins. To truly see a snowflake, we must learn to see with new eyes. We must imagine ourselves shrinking down, smaller and smaller, until we are no bigger than the molecules themselves. At this scale, the world transforms completely. What seemed solid and static reveals itself to be dynamic and dancing. The snowflake is not merely a pretty shape. It is a record, a three-dimensional diary of every moment. The crystal spent growing in the sky. Each branch, each plate, each needle tells us about the temperature and humidity it encountered. Can you imagine? A snowflake is a tiny weather station carrying data from the heavens. Let us begin this journey properly, from the absolute beginning. We will start with the simplest building block, the humble water molecule, and trace its path from invisible vapor to intricate crystal. Along the way, we will discover why ice insists on forming hexagons, why temperature determines shape, and why no two snowflakes can ever be truly identical. This is not just science. This is poetry written in physics, beauty emerging from mathematical necessity. Take a deep breath, settle in, and prepare to see winter with completely new understanding. As we prepare to dive deeper, remember this. Everything we are about to explore happens silently, invisibly, billions of times every winter day. Right now, as you listen to these words, snowflakes might be forming somewhere in the world, each one going through this ancient process. They do not need us to observe them or understand them. They simply exist, perfect and temporary, whether anyone watches or not. But we are going to watch. We are going to understand. And in doing so, we might just discover something about the nature of beauty itself. Let us begin with water, that most familiar substance. You drink it, bathe in it, swim in it. It covers most of our planet and makes up most of your body. Water is so common that we rarely stop to consider how extraordinary it really is. But water is weird. It expands when it freezes, unlike almost every other substance. Ice floats on water, a property that allows fish to survive winters in frozen lakes. And water can exist in all three states within the narrow range of temperatures found on Earth. All of these strange behaviors come from one thing, the shape of the water molecule itself. Imagine yourself at the molecular scale, floating in space among water molecules. What would you see? Each water molecule consists of just 3 atoms. One oxygen atom sits at the center, large and electronegative, with 2 smaller hydrogen atoms bonded to it. But here is the crucial detail. These atoms do not arrange themselves in a straight line. Instead, they form a bent shape like a boomerang or the letter V. The angle between the 2 hydrogen atoms is about 104 degrees. This angle, this specific geometry, determines everything that follows. Why does this angle matter so much? Because it creates polarity. The oxygen atom hoards electrons, pulling them away from the hydrogen atoms. This makes the oxygen side of the molecule slightly negative, while the hydrogen side becomes slightly positive. The water molecule becomes a tiny magnet with a positive end and a negative end. Now imagine billions of these tiny magnets floating near each other. What happens? They attract. The positive hydrogen of one molecule reaches toward the negative oxygen of another. This attraction has a name that will become very important. We call it hydrogen bonding. Hydrogen bonds are remarkable things. They are not as strong as the bonds that hold the atoms within each molecule together, but they are strong enough to give water its unique properties. In liquid water, these bonds constantly form and break and reform, creating a dynamic dance of molecules sliding past each other. But what happens when we cool water down? What happens when we remove energy from this molecular ballet? The dance slows. The molecules move less frantically. And at a certain temperature, something magical occurs. The hydrogen bonds begin to lock into place, forming a stable, repeating pattern. We call this pattern ice. But ice is not just frozen water in some generic sense. The hydrogen bonds arrange the water molecules into a very specific pattern, a pattern with mathematical elegance. Each oxygen atom positions itself at the center of a tetrahedron, surrounded by 4 other oxygen atoms. Think of it like a 3-dimensional dance where every dancer maintains the same distance from their 4 nearest partners. This tetrahedral arrangement repeats throughout the ice crystal, creating a regular, repeating structure. And here is the key. This tetrahedral geometry naturally produces hexagonal symmetry when viewed from certain angles. The hexagon is not an accident. It is a necessity born from the shape of the water molecule and the geometry of hydrogen bonding. Take a moment to appreciate what this means. The 6-sided symmetry you see in every snowflake, that perfect hexagonal form, is not designed by nature. It is not random. It emerges inevitably from the quantum mechanical forces governing how atoms bond together. The same forces that determine the angle between hydrogen atoms in a water molecule also determine the shape of a snowflake visible to your naked eye. From the smallest scale to the scale you can see, the same rule applies. This is one of the most beautiful aspects of physics. The micro determines the macro. The invisible shapes the visible. And water, simple water, demonstrates this truth with crystalline perfection. High in a cloud, the air is saturated with water vapor. The molecules drift freely, colliding with air molecules, bouncing and tumbling through space. The temperature up here is well below freezing, cold enough that you might expect the water to freeze instantly. But it does not. This is one of the peculiar facts about water. It can remain liquid or vapor well below its freezing point if conditions are just right. We call this supercooling. The water wants to freeze, but it cannot quite manage it alone. It needs help. It needs something to freeze onto. It needs a seed. What can serve as a seed for ice crystal formation? Many things, it turns out. A tiny speck of dust, a grain of pollen, a microscopic fragment of clay blown up from deserts far below. Even bacteria can serve as ice nuclei. These particles provide a surface, a template upon which water molecules can begin to arrange themselves. Without these seeds, clouds could remain supercooled indefinitely. But with them, the transformation begins. A single water molecule touches the particle. Then another, and another. The hydrogen bonds start to form, locking into that tetrahedral pattern we discussed. The ice crystal has begun its life. This initial seed crystal is incredibly small, far too tiny for you to see even with a microscope. But it contains the blueprint for everything that will follow. The hexagonal symmetry is already present, encoded in those first few molecular layers. As more water vapor molecules collide with the growing crystal, they stick preferentially to certain spots. The crystal does not grow uniformly in all directions. Instead, it develops facets, flat surfaces where the molecular packing is most stable. These facets reflect the underlying hexagonal symmetry. The crystal begins to take on shape. At this stage, the young crystal is still essentially just a hexagonal prism, a tiny column with 6 sides. It might be only a few micrometers across, invisible to your eye but massive from the perspective of individual molecules. This is the foundation, the core around which everything else will build. The crystal will carry this hexagonal seed within it for its entire existence. Every branch, every plate, every intricate detail that develops later will maintain this 6-fold symmetry because it was present from the very beginning. The architecture was determined in the first moments of formation, but the crystal does not stay simple for long. As it continues to grow, something interesting happens. The corners of the hexagon, the 6 vertices where the faces meet, become sites of rapid growth. Why? Because water molecules arriving at these corners can form more hydrogen bonds than molecules landing on the flat faces. The corners are energetically favorable. They are where the action happens. As vapor molecules preferentially stick to these corners, 6 tiny bumps begin to form, one at each vertex of the hexagon. These bumps are the beginning of branches. The snowflake is starting to develop its characteristic form. Now, the crystal is becoming recognizable as a snowflake. It has a center and 6 budding arms, each one a mirror image of the others. The hexagonal symmetry is preserved because each arm experiences essentially the same growing conditions. They are all part of the same tiny crystal, tumbling together through the same parcels of air, exposed to the same temperature and humidity. What affects one arm affects them all equally. And so they grow in unison, maintaining their symmetry even as they become more complex. This is the moment when a simple ice crystal transforms into something that looks like the snowflakes you know. The architecture is emerging. Why? 6? This question has fascinated people for centuries. Long before anyone understood molecular structure, observers noticed that snowflakes always have 6 sides or 6 arms. Or never 5, never 7. It's me, always 6. Ancient philosophers wondered if this was evidence of divine geometry, a sign that the universe itself was constructed according to mathematical principles. They were closer to the truth than they knew. The 6-fold symmetry is indeed a law, but it is a law of physics and chemistry, not divine decree. It is the inevitable consequence of how water molecules bond together. Remember the water molecule and its bent shape, that crucial angle of about 104 degrees. Now imagine trying to arrange these molecules in a flat plane, each one hydrogen bonding to its neighbors. Its pattern emerges. If you work through the geometry, you find that the molecules naturally arrange themselves into rings. And the most stable ring, the one that allows all the hydrogen bonds to form with minimal strain, contains 6 water molecules. A hexagonal ring. This is the fundamental unit of ice's structure. Stack these hexagonal rings on top of each other, and you get the three-dimensional lattice of ice. The hexagon is not chosen. It is required. This hexagonal lattice has profound consequences. When you look at a snowflake from above, you are looking down one of the crystallographic axes of the ice lattice. You are seeing the molecular arrangement itself, magnified 1,000,000 times. The 6 arms of the snowflake point along directions where the crystal can grow most easily, where adding new molecules is energetically favorable. These directions are determined by the lattice structure, which is determined by the molecular geometry, which is determined by quantum mechanics. From the quantum to the macroscopic, everything connects. The snowflake is a visible manifestation of invisible laws, but we should be precise here. Not all ice crystals show six-fold symmetry so obviously. Sometimes crystals grow as simple hexagonal columns or plates. Sometimes they develop hollow cores or form needles. The underlying lattice is always hexagonal, but the visible shape depends on exactly how the crystal grows, which in turn depends on temperature and humidity. Still, even when the six-fold symmetry is not obvious at first glance, it is always there if you look closely enough. Every snowflake, every ice crystal bears the signature of the hexagonal lattice. It cannot be otherwise. The laws of physics do not allow exceptions. Consider for a moment how remarkable this is. Every snowflake that has ever fallen anywhere on Earth throughout all of history has been hexagonal. The snowflakes that fell on dinosaurs were hexagonal. The snowflakes that will fall 1,000 years from now will be hexagonal. This is a constant, a universal truth as reliable as gravity or the speed of light. And yet it emerges not from some cosmic decree, but from something as simple as the shape of a water molecule. The universe builds grand patterns from humble foundations. The complex arises from the simple. And we, observing snowflakes on a winter day, are witnessing the same molecular dance that has been performed for as long as there has been water and cold. The six-fold symmetry also explains something else you may have noticed. Snowflakes often look like they have 12 or even more divisions, not just 6. But look carefully, and you will see that this is an illusion created by the arms and their branches. The fundamental symmetry is still sixfold. Some snowflakes develop branches that sprout from the main arms, creating additional detail. Some have ridges running between the arms. But all of these features respect the underlying sixfold pattern. The snowflake can elaborate on its basic theme, but it cannot escape it. The hexagon is its destiny, written into its molecular structure from the first instant of formation. Now our snowflake is growing in earnest. It has established its hexagonal symmetry and begun to extend its 6 arms into the surrounding vapor-rich air. But growth is not a smooth, steady process. It is more like a dance, a back and forth between the crystal and its environment. Water molecules arrive at the crystal's surface and stick. Some positions are more favorable than others. Corners and edges attract more molecules than flat faces. And so the crystal develops texture, complexity, features. It becomes more than just a hexagon. It becomes architecture. One of the most striking features of snowflakes is their branching. The main arms often develop side branches, which in turn can develop their own smaller branches, creating intricate dendritic patterns. The word dendritic comes from the Greek word for tree, and it is apt. A snowflake with well-developed branching looks remarkably like a leafless tree seen from above. But what causes this branching? Why does not the snowflake simply grow as six smooth spikes? The answer lies in an instability that occurs during crystal growth. When an arm is growing, any tiny bump or irregularity on its surface tends to capture more vapor molecules than the smooth areas around it. The bump grows faster. It becomes more pronounced. Eventually, it becomes a side branch. This process, called the Mullins-Sakirka instability, is responsible for much of the beauty we see in snowflakes. It is a form of positive feedback. Now, growth begets more growth. Small differences become amplified. And because the entire crystal experiences the same conditions, the same process occurs on all six arms simultaneously, maintaining symmetry even as complexity increases. Each arm develops branches at roughly the same positions and times as the other five. They remain coordinated even though they are not directly connected. They grow together, responding to the same environmental cues, creating a unified structure of astonishing intricacy. But not all snowflakes develop branches. Some remain relatively simple, growing as hexagonal plates or columns. What determines whether a snowflake will be simple or complex? The answer is fascinating. It depends primarily on temperature. At certain temperatures, plate-shaped crystals form. At other temperatures, columnar crystals grow. And at still other temperatures, particularly around -15 degrees Celsius, the conditions favor the formation of the elaborate dendritic crystals that we find most beautiful. There is a morphology diagram, a map that shows which crystal shapes form at which temperatures and humidity levels. It is like a guidebook to the taxonomy of snowflakes. As our snowflake grows, it is also falling. It drifts downward through the cloud, slowly at first, then faster as it accumulates mass. And as it falls, it experiences changing conditions. The temperature shifts. The humidity varies. Change affects how the crystal grows. A warmer layer of air might favor plate growth, adding flat facets to the arms. A colder layer might promote dendritic branching, adding intricate detail. The snowflake's final form is thus a record of its journey through the atmosphere. It is a tiny archive of meteorology, preserving information about the cloud in which it formed. When you look at a snowflake structure, you are reading the story of its descent. This is why snowflakes are so varied. Two crystals might begin growing at nearly the same time and place, but take slightly different paths through the cloud. One might drift through a pocket of higher humidity. Another might tumble through a warmer layer. These small differences accumulate, leading to different growth patterns, different branch formations, different final forms. And because the number of possible paths through a cloud is essentially infinite, and the variations in temperature and humidity are continuous rather than discrete, the number of possible snowflake forms is also infinite. This is the root of the snowflake's uniqueness. Not randomness, but rather the amplification of tiny environmental differences through the growth process. Let us explore this relationship between temperature and form more deeply, for it is one of the most elegant aspects of ice crystal physics. Water molecules approaching a growing crystal face have kinetic energy related to the temperature. At higher temperatures, they move faster, vibrate more. Lower temperatures, they slow down. This affects how they incorporate into the crystal lattice. A molecule that lands on the crystal might stick immediately, or it might slide around on the surface for a moment before finding a good binding site. The temperature determines how mobile these surface molecules are and this in turn affects which crystal faces grow fastest. At temperatures just below freezing, around -2 to -5 degrees Celsius, ice crystals tend to grow as thin hexagonal plates. These are flat snowflakes, like little ceramic tiles falling from the sky. The molecules at these temperatures favor adding to the two large flat faces of the crystal rather than to the edges. The result is a crystal that grows wider but not thicker. If you were to catch one of these plate crystals on a dark surface, you might see just a tiny hexagonal outline, elegant in its simplicity. These are the crystals that create the soft crunching sound when you walk on fresh snow, thousands of tiny hexagonal plates compressing and breaking underfoot. Drop the temperature a bit more to around -5 to -10 degrees Celsius, and something changes. Yow, columns start to form. These are snowflakes that grow longer in one direction, like tiny pencils or pillars. The molecules at these temperatures prefer to add to the ends of the crystal rather than the sides. Some column crystals are simple hexagonal prisms. Others become hollow, developing a depression or cavity at each end. These hollow columns have a particular kind of austere beauty, like miniature crystalline tubes. They rarely show the elaborate branching of stellar dendrites, but they possess their own minimalist elegance. But here is where it gets truly fascinating. Lower the temperature to around -12 to -16 degrees Celsius, and suddenly we enter the realm of the stellar dendrites. These are the snowflakes that everyone thinks of when they imagine snowflakes. 6 long arms radiating from a central hexagon, each arm covered with elaborate branching and sub-branching, creating fractal-like patterns of stunning intricacy. At these temperatures, growth at the corners and edges is strongly favored, and the instability that causes branching becomes very pronounced. The crystals become works of art, nature's finest examples of spontaneous pattern formation. If you want to see spectacular snowflakes, you need to wait for nights when the temperature hovers in this magical range. Go colder still, below -16 degrees, and plates return. But these are different from the plates at warmer temperatures. These are often sectored plates with triangular markings on their faces. The pattern continues, alternating between plate-like and columnar forms as temperature drops. Why does this happen? Why does ice switch back and forth between growth modes? The full answer involves complex surface physics and is still an area of active research. But the pattern itself is clear and reproducible. Temperature is the master sculptor, determining the broad form of the crystal. Humidity and other factors add the details, but temperature sets the stage. This temperature dependence means that snowflakes falling in different parts of a storm can look quite different. The crystals forming high in the cloud, where it is coldest, will have one morphology. Those forming lower down, in warmer air, will have another. And as crystals fall through temperature layers, they can develop composite forms. You might see a snowflake with a columnar center and plate-like ends, recording in its structure the journey from cold to warmer to cold again. Each snowflake is thus not just a crystal, but a narrative, a tiny history book written in ice. The architecture tells the story of the atmosphere itself. While temperature determines the basic form of a snowflake, humidity plays a more subtle but equally important role. Humidity refers to the amount of water vapor present in the air. In a cloud, we typically talk about supersaturation, which means the air holds more water vapor than it can normally sustain at that temperature. The excess vapor wants to condense, and ice crystals provide the perfect surface for that condensation to occur. Higher supersaturation means more vapor molecules are available to join the growing crystal. This affects the rate of growth and the level of detail that develops. At low supersaturation, crystals grow slowly. There simply are not enough vapor molecules arriving at the surface to build elaborate structures quickly. The crystals that form tend to be simpler, with less branching and fewer fine details. They have a spare, minimalist beauty. Think of them as ice haiku, saying much with very little. But increase the supersaturation and everything changes. Now vapor molecules are abundant. They arrive at the crystal surface in a rush. Growth accelerates. The instabilities that cause branching become more pronounced. Fine details develop. The crystal becomes ornate. There is a sweet spot, a combination of temperature and humidity that produces the most spectacular snowflakes. Around -15 degrees Celsius with high supersaturation, the conditions are perfect for creating large stellar dendrites with extensive branching. These are the snowflakes that grace holiday cards and decorations. They represent ice crystal growth at its most exuberant, nature showing off its ability to create pattern and structure from nothing but water and cold. If you are a snowflake photographer, these are the conditions you hope for. These are the nights when magic happens, but humidity does something else interesting. It affects how quickly a crystal grows relative to its neighbors. In a cloud with many growing crystals, they all compete for the available water vapor. A crystal that gets a head start, perhaps because it nucleated earlier or started in a vapor-rich pocket, will grow larger. As it grows, it depletes the vapor in its immediate vicinity. Nearby crystals find less vapor available and grow more slowly. This creates a size distribution. Some crystals become large and elaborate. Others remain small and simple. The big get bigger while the small stay small. It is a kind of competitive growth, though the crystals themselves have no awareness or intent. Humidity can also affect the transparency and clarity of the ice. Very slow growth from low supersaturation tends to produce clear, glassy crystals. The molecules have time to find their optimal positions in the lattice, creating a nearly perfect structure with few defects. But rapid growth from high supersaturation can trap air bubbles or incorporate impurities. The crystal becomes cloudy or opaque. Sometimes the center of a snowflake is cloudy while the arms are clear, recording a change in growth conditions. The crystal becomes a record not just of temperature, but of how much vapor was available at each stage of its development. Understanding the interplay between temperature and humidity gives us predictive power. Scientists have created detailed morphology diagrams that map crystal type to these two variables. Given a temperature and supersaturation, we can predict what kind of snowflake will likely form. And inversely, by examining a snowflake's structure, we can infer something about the conditions it experienced during growth. This makes snowflakes useful as atmospheric probes. They carry information from high in the clouds down to the ground where we can study them. Each crystal is a tiny data package encrypted in ice, waiting to be decoded. We have now explored the principles that govern snowflake formation. We understand the hexagonal symmetry, the role of temperature, the influence of humidity. But one question remains, perhaps the most intriguing question of all. Why is every snowflake unique? How can a process governed by physical laws produce infinite variety? The answer lies in the extraordinary sensitivity of crystal growth to initial conditions and environmental variations. A snowflake's path through the atmosphere is never quite the same as any other, and tiny differences in that path lead to differences in form. Consider two snowflakes forming at nearly the same moment in the same cloud. They might start just millimeters apart, but as they grow and fall, they diverge. One drifts slightly to the left, the other to the right. One encounters a microscopically warmer parcel of air. The other passes through a region with slightly higher supersaturation. These differences might seem trivial, almost insignificant. But remember, crystal growth is a process with positive feedback. Small differences get amplified. One crystal develops a branch slightly earlier than the other. That branch grows, creating its own side branches. the pattern diverges further. By the time they reach the ground, the two crystals look completely different. This is similar to chaos theory, the idea that small changes in initial conditions can lead to vastly different outcomes. The famous example is the butterfly effect, where a butterfly flapping its wings in one part of the world can theoretically influence weather patterns weeks later on the other side of the globe. Snowflake growth is not quite as chaotic as weather, but it shares this sensitivity to minor perturbations. The growth of ice crystals is deterministic, meaning it follows precise physical laws, but it is not predictable in practice because we cannot measure all the tiny variations in temperature and humidity that the crystal experiences. We know the rules, but we cannot predict the outcome. Nay. How many possible snowflake forms are there? The number is not literally infinite, of course. There is a finite amount of matter in the universe and a finite amount of time. But for all practical purposes, we can treat the number as infinite. Some scientists have estimated that the number of possible snowflake configurations exceeds the number of atoms in the known universe. That is a staggering thought. It means that in all likelihood, every snowflake that has ever fallen was unique. Every single one. And every snowflake that will ever fall in the future will also be unique. You will never see the same snowflake twice. Nature does not repeat itself at this scale. This uniqueness is not just a curiosity. It tells us something profound about nature. It shows us that deterministic laws can produce endless variety. You do not need randomness to get diversity. You just need sensitivity to conditions and a complex growth process. The universe is capable of creating novelty within constraints. The rules of ice crystal formation are rigid and unchanging. Hexagonal symmetry is mandatory. But within those rules, there is room for infinite expression. It is like music, where 12 notes can be combined in endless ways to create infinite songs. Or like language, where an alphabet of letters produces infinite texts. The constraints do not limit creativity. What? They enable it. When you hold a snowflake on your glove for those few seconds before it melts, you are holding something that has never existed before and will never exist again. It formed minutes or hours ago in a cloud above you. It fell through cold air, experiencing conditions unique to its particular trajectory. It landed on your hand by pure chance. And now it is melting, returning to water, its structure dissolving back into disorder. The snowflake's existence is brief, but it was real. For a moment, this particular arrangement of water molecules existed, this particular pattern manifested in ice. And then it was gone. There is a kind of poignancy to that ephemeral existence, a reminder that beauty need not be permanent to be meaningful. As we near the end of our journey through the world of snowflakes, let us step back and consider the bigger picture. Why does any of this matter? Why should we care about the molecular structure of ice or the formation of snowflakes? One reason is pure wonder. The beauty and complexity of snowflakes are worth appreciating for their own sake. But there is more to it than that. Water and ice are fundamental to life on Earth. Understanding their properties helps us understand our planet, our climate, and even ourselves. We are, after all, mostly made of water. The same molecules that form snowflakes also form tears, blood, and the fluid inside every cell of your body. Water's ability to exist in 3 states at Earth's temperatures is crucial for life. The water cycle, driven by evaporation, condensation, and precipitation, redistributes fresh water across the planet. No fall in mountains becomes the source of rivers and streams that sustain ecosystems downstream. Ice sheets and glaciers store vast quantities of fresh water, releasing it slowly over seasons and years. Without ice's peculiar property of floating on liquid water, lakes would freeze from the bottom up, killing aquatic life in winter. The same hydrogen bonding that creates snowflake symmetry also makes water an excellent solvent, allowing it to transport nutrients and minerals. Ice and water together make Earth habitable. Studying snowflakes also teaches us about cloud physics and weather prediction. Clouds contain millions of tiny ice crystals and water droplets. How these crystals grow and fall affects whether a cloud produces rain or snow, and how much precipitation reaches the ground. Understanding ice crystal formation helps meteorologists improve forecast models. It helps climate scientists predict how clouds will respond to warming temperatures. Clouds play a complex role in Earth's energy balance, reflecting sunlight and trapping heat. The tiniest details of ice crystal physics can have global implications. A snowflake is not just a snowflake. It is a component in a planetary system. There is also something to be learned about pattern formation and self-organization. Snowflakes form without any external blueprint or instruction. No one tells the water molecules where to go or how to arrange themselves. They simply follow local rules, responding to their immediate environment, and yet somehow collective order emerges. A complex, symmetrical structure appears spontaneously. This kind of self-organization is common in nature. It happens in crystal formation, in the spirals of seashells, in the branching of trees and blood vessels, even in the folding of proteins. By studying snowflakes, we gain insight into a fundamental principle of how complexity arises from simplicity throughout nature. On a personal level, snowflakes remind us to pay attention. In our busy lives, we often rush past small wonders. A snowfall becomes just an annoyance, something that slows traffic or requires shoveling. But if you stop and look closely, if you catch a few flakes on a dark surface and really examine them, you will see intricate structures that rival any human art. You will hold in your hand something that has never existed before. This practice of noticing, of slowing down to appreciate tiny marvels, is valuable in itself. It cultivates mindfulness and wonder. It reminds us that the universe is full of beauty at every scale, if only we take the time to look. Finally, snowflakes teach us about transience and impermanence. Their beauty is inseparable from their brevity. A snowflake exists as a distinct crystal for minutes or at most hours. Then it melts or sublimes, returning to vapor or liquid. Its structure is lost forever. This ephemeral quality does not diminish the snowflake's beauty. If anything, it enhances it. We treasure things more, knowing they will not last. The Japanese aesthetic concept of mono no aware captures this poignancy, the bittersweet appreciation of transient beauty. Snowflakes embody this perfectly. They are exquisite precisely because they are fleeting. And perhaps we too find meaning, not despite our mortality, but because of it. Our journey into the architecture of a snowflake comes to a close. But the winter sky continues its work. Right now, somewhere above us or above another part of the world, new crystals are forming, growing, falling. Each one is a unique expression of water's molecular nature, a temporary sculpture in ice. The next time snow falls, I hope you will see it differently. Not just as frozen water, but as countless tiny messages from the clouds, written in hexagonal geometry. One if you can. Look closely. Look closely. And know that you are seeing something that has never been seen before and will never be seen again. That is the gift that winter gives us. Thank you for joining me on this quiet exploration. Until next time, stay curious and stay calm.